So in the session that we had in the last class, we started talking about the probability of default under the Basel models, right? So what was the probability of default that we were talking about? So probability of default, as we said, is probably the chances of a borrower to default in the next 12 months, right? And what we wanted to do over here is we wanted to understand the challenges, or what we want to do was we wanted to understand the challenges of developing this model. But before that, we started exploring what exactly is probability of default and how is it that we could actually use the probability of default in understanding, or how is it that we could actually try and understand what is default and what is probability of default. So we saw that in Basel, the regulation that we started talking about in Basel, a default was or an account was considered to be a default if it had the following characteristics, or if it satisfied one of the following characteristics, which was either the account was 90 days past due, or it was written off, or it was a restructured loan account, or it was a payment plan. So over here, according to the Basel criteria, I believe that any one of if the account status fell under any one of these categories, it would be considered as a defaulted account, right? Now, this set of defaults. Now, over here, we are solely concerned with this set of defaults, the account defaults that has happened. The first set of default that has happened was, or when we talk about a set of defaults, uh, the question that comes out is that how and where are these defaults considered, right? So basically, when we are developing a probability of default model, right, a PD model, our objective is to assess the chances that an account will default in the next 12 months, right? So that is what our first objective is. The second case, or in the second case, what we want to do is we want to understand that is that okay, if this account go into default in the next 12 months, what would be their estimated exposure? So over there, we are trying to understand the exposure that a respective account would have at default. And third, what we are doing is we are talking about the chances that the borrower would, and third, that if a borrower has gone into default, what are the chances that there would be some recovery from there, and what would be the loss given default, right? So over here, so over here, what we are trying to do is we have started analyzing from the first question, the first point, that is I have a set of accounts and I want to understand that how many of those accounts or what exactly are the chances of the account to default in the next 12 months. So over here, what I need to understand is that what are the set of accounts or what are the set of observations to which we are looking into. So the set of observations that we are looking into are the set of active accounts, accounts which have still not defaulted. So accounts which may go into default in the next 12 months, right? So this is what the observation is. Also, this is what the base should look like. So when we are trying to develop a PD model, right? So our objective over there would be to develop a model on the set of accounts which are active and which remain active in the next 12 months. So they may go default, but they are not written off the books, right? So if they so accounts which satisfy any one of the default definitions are considered to be off-book accounts. We are not in a position to consider off-book accounts. So when we are developing the PD model, we are always considering the on-book accounts. So I'll just come over this once again. When I'm trying to assess the probability of default, when I want to understand whether a borrower will default or not, what are the chances of a borrower to default, then I'll be considering the set of those accounts which are non-defaulters. So the accounts which have not defaulted but are active on the book of the bank. Now, if an account has defaulted, then there is no point in assessing its chances to go bad. I will assess its chances to go bad if and only if the account is active. If it's already defaulted or it's going bad, then that's okay, right? So over here, what we need to understand is that if I'm standing today, right? So I need to ensure that the account is active today, and I'm ensuring that the probability to default over the next 12 months. I'm trying to assess the probability of a borrower to default in the next 12 months. So that means I should also ensure that this account that I'm considering for model development is active in the next 12 months as well. Right. So in the historical data, when I'm developing the model, when I'm creating my dependent variable flag, I need to ensure that the account that I'm using to develop my model must be active in the next 12 months as well, because I'm trying to always predict whether the borrower is uh, defaulting in the next 12 months or not. So to assess this probability, I need to ensure that the model is developed in the next 12 months, right? Anirudh, is it clear? Great. So over here, what we started doing off in the last class was we started talking about what exactly is this probability of default. So what exactly is the theory behind this probability of default, or how is probability of default theoretically structured? So that is what we started doing off in the last class. And in an attempt to do that, right? So we came across the concept of, so we started talking about an obligor I. So for an ith obligor, right, there is an asset. So every obligor has an asset, right? So as if I'm a retail borrower, I'll have a income, I'll have income from other sources, etc. And I have a debt obligation DI. So AI shows the asset that the borrower I has. Now it is more relevant. So this representation will be more relevant for commercial portfolios, where we talk about the probability of a borrower of being, you know, where we talk about the asset, and the asset of the borrower fluctuates over a period of time. So what we say over here is that AI is the asset of the borrower, and for a retail portfolio, the fluctuation in the asset is relatively lower, right? And DI is the debt obligation. So over here, the default occurs if and only if the AI or the asset of the ith observation is less than the debt obligations, or rather the debt or the loan that the guy has taken. So if the asset falls below the debt amount, the borrower would default. So whenever I am trying to assess this, right, I am trying to assess the probability that the ith borrower may default in the next 12 months. So what is the probability that in the next 12 months the asset of the borrower falls below the debt obligation that he has, or the outstanding obligation that he has? Now, the theoretical framework, right, on which this prediction, or the theoretical framework on which this entire concept stands, is nothing but it's extracted from an actuarial model. So the structural credit risk model that on which the entire Basel framework stands So Basel is a kind of a structural credit risk model framework. So in the structural credit risk model framework, what we get to see is the following: that the borrower, so in the structural credit risk models, now this genre of models has been extracted or has been borrowed from the actuarial models of models like option pricing, derivative pricing, and so on. And from there, what you have is you have the Black-Scholes, and this model that we talk about, or the model that we would be talking about going forward, is a variant of the Black-Scholes-Martin 1976 option pricing model. So this was the very same model for which Black-Scholes and Martin were awarded the Nobel Prize. And later, this framework was used by Vasicek in 1987 to create a framework which is known as the asymptotic single risk frontier model, right? And it showed that there is only one source of risk which impacts the risk both at the portfolio and at the account level. That is why we can, that is why, and it is this assumption, it is this model which ensures that at portfolio level, you can do account level aggregation. So I can compute out the probability of default for a representative account, read all the accounts, find out the expected losses for each of the portfolios, say credit risk, for credit cards, personal loans, for mortgages, pull them up at a retail level, then do it for commercial, pull them up at a commercial level, then pull them up at a branch level, then pull all the branch levels up at a organization or a bank level. So that is how this entire aggregation can actually happen. So this is what we were trying to understand, right? So it is, so the very background of this model, or the very basic, the result on which the entire Basel model stands is the asymptotically single risk frontier model, right? So this is how the model. So this is what the mod or so this is what the basic assumption is, and what we would do is, or what we would talk about is, we would talk about creating, or we would try to understand how this model is framed, right? And so first of all, what we need to understand is how this particular model is framed. So over here, the basic point from where this equation or this model starts is the asset price dynamics. So gradually as we move ahead, we would be covering conditional PD, unconditional PD, through the cycle PD. We'll talk about point in time PD and so on. And all this would be done in reference to this Vasicek model. So over here, the first thing that we start up our discussion with over here is the asset price path, asset equation. The first equation that we start off with is the asset price equation. Now the question that comes out over here is that what exactly is this asset price equation? So this is DAT by AT. So what is DAT by AT? So if I interpret this is nothing but, very simply spoken, this is nothing but the percentage change in price. The percentage change in the asset price. In the asset price. So what is percentage change in the asset price? Percentage change is change in asset price divided by the asset price. This is what is percentage change in the asset price. Now the percentage change in asset price is defined by two components. So this is mu APD plus sigma A DW. So this is what the asset price equation is. So let us first of all try to understand what this particular part is all about. What is this mu A? What is sigma A? What is dWAT? What is this? What does this mathematical equation mean? Now this is a very interesting mathematical equation with a very simple intuitive explanation. Let's consider the asset price part. Right. So how would it look like for a business? So this is say time. So over here, what we want to know is that over time, how does the asset price path change? Zero. And over here is your asset price, asset at time. So over here, what we have is the following. Say this is a business, okay? So this owner or this obligor is a commercial obligor. If he's a commercial obligor, what are the things that are going to happen over here? So obviously his business would fluctuate, right? About a mean value, but they will fluctuate. This is how it will go, right? But the fluctuation will always happen about a given point or will happen about a given average value. So that average value is this, right? So it will happen about a given average value. So what we'll get to see over here is the following. So what I have is a asset price path, right? And this asset price path is something which will have, or which we'll talk about. So it will be represented by its average, right? And this average or this line of average that I have over here is my mu A. So it says that the average price path, right? So the average percentage change in price will always fluctuate about an average percentage change in price. So on a per unit basis, there would be an average fluctuation, right? So over here, what you see is that this mu A that I get to see over here talks about the average percentage change. The average percentage change in the asset price or in the asset value. Asset value. Value per unit of time. Per unit of, right? So this is the average change in the asset value per unit of time. Now over here, the mu A is, so over here what I'll have is the mu A is the average change per unit of time. Now what is this dt? What is dt over here? dt is the total change in time. The total change in time period. It is the total change in time period. In time period. So this is what is the overall idea, that there is a total, so there is a total change in time period. Now what does these two parts mean together? Say for example, over here I say that mu A is 5%. So what I am saying is that in a time period the asset price generally changes up or down, whichever way it may be, by 5%, right? So now mu A is 5%, that is the percentage change in time period is 5%. Now I ask you that, okay, if the average percentage change in the price of the asset is 5% in a period, then in 2 years, what will be the, in the next 2 years, what will be the percentage change in the asset's price or in the asset's value? So the next 2 years is, so I'm standing today, that is time period T, and the dt is 2. So what I want to know is that when the time period changes by 2 years, what will be the change in the asset price? So the total change that I'll observe in the asset price is mu A dt. That is 5% into 2. That is 10%. So what I'll say is that in the next 2 years, the average change in the asset price would be, or the average value of the asset would be 10%. So this shows the total change, the total average change in the asset price. So this mu ADT shows the total average change, the total average change in the asset price. In the asset price, right? So total average change in the asset price. So over here, what we say is that the total change in the asset price is first of all is driven by the average change in the asset price, right? So that's the first thing. So this is where, so this is what the line is. Now we observe that this is the average value or the average change, right? But the actual price change is not driven by only averages. There is a movement associated with it about the average. Now, if there is a movement associated about the average, how will I take care of that? So that is taken care of by the standard deviation. So what is the standard deviation? The standard deviation sigma A, or whatever we call it, right? So sigma A measures the average spread in the distribution. It measures the average spread of the distribution. Spread of the distribution. Spread of the distribution. So sigma A measures the average spread of the distribution. How is it defined? Sigma is nothing but the standard deviation and is defined as 1 by n summation xi minus x bar whole square. So it is the sum square deviation about the mean. Clear? So this part is sigma A. That is 1 by n summation I1 to n xi minus x bar whole square. Right? So it is generally the square root of this. So xi, as we call it, it is the observation. Say, for example, I have 10 values in the variable contain 10 values, right? So x1 is the first value of that variable x. So for example, I have a variable x like this. right? So which contains values. This 2, 3, 4, like this. So this is something which I can call x1 in the general form. So the first value that the variable x takes. This is x2, which is the second value which the variable x takes, and this is x3, which is the third value which the variable x takes. These are the different values. So what I'm saying is that the standard deviation is the measure of the overall variation from the mean, right? So it gives us an overall idea about the dispersion from the mean. Great. So now over here, if we think about this sigma A, so sigma A gives us an idea about the overall dispersion from the mean, the overall fluctuation from the mean that I have, right? So over here, when I have this fluctuation about the mean, right, the next question that comes out to us over here is that, but this fluctuation is an average value. So this measure is an average measure of dispersion, right? So this is an average. And since it's an average, it's an average. And since it's an average, it is a constant value. So it is a constant value. Now, if I think about this in a manner, right, you'll see that. So this is a constant value, but the deviation that happens, right, that happens, there are, so the deviation that happens, that's not constant, right? It can happen in different amplitudes. Say there can be some periods where there are relatively higher variations than periods where there are relatively lower variations. So what I need to do is I need to bring in a kind of, so there is some randomness associated with that amplitudes of variation. The average variation is sigma A, so that's the average value of the variation. But that average value fluctuates over different points of time because there, depending on the businesses, there can be lower fluctuation. When there is a downturn, there would be a relatively higher fluctuation and so on, right? So we need to create this. So basically there is, if you observe over here, you will see that there is a randomness. So there is a randomness among the values, among the variations. So sigma A captures on the average variation, but it does not contain the randomness of the variation. Now, if I define it as a just as a constant variation, that would be difficult because there is a constant fluctuation about this. So over here, what we use is the Wiener process. Now the Wiener process helps us specify a random or a Brownian motion. It's a Wiener process. So over here, if I'm talking about a Wiener process, right, I'm talking about a random, or as we call it, a Brownian motion. And W is the Wiener variable which represents this Brownian motion. So now this is where the entire story in this equation changes. So what exactly is a Wiener process? Where what exactly is a Brownian motion? How can a letter explain a Brownian motion? So these are the questions that obviously comes up, because people who have had science in their 10 class 10s and 11s in their high schools, you guys would be very aware of what the Brownian motion is, right? So it's a motion of randomness. So we used to study this talcum powder case. So it says that if you take a bowl of water, right, and you sprinkle talcum powder on that, so that powder particles will float, and they will follow a very random kind of a motion, and that motion is called a Brownian motion, right? And it's a very deterministic randomness, because you do not have any external shocks coming in and anything. So it is just because of the fluid's movement that this thing is moving about. So that is what is your Brownian motion. Now, Brownian motion for us in most of these financial variables, right? See, there is considerable amount of randomness which is involved into this, right? So therefore, we call it. So this part will be your Brownian motion. So what exactly is Brownian motion over here? What did we talk about? What is Brownian motion at the end of the day for us? For us, it is nothing but it's a measure of the randomness. Randomness. So there is Brownian motion and then there is randomness. So when I talk about randomness, or say for that matter, when I talk about Brownian motion and all, so what is it that so what is it that we are trying to do over here? We need randomness, because as you can see, if you look into this diagram, into this graph, you see that the variations are not same everywhere. So there are certain random movements. So there are certain random changes. So this DW80 shows the random changes in sigma A. So, but before we go into that, let us understand what is this WA. What is this W? Now, W is known as, is very famously known as the Wiener process. WA is Wiener. Is the Wiener process. Wiener process. The Wiener process is nothing but it's a random variable. A variable which has different outcomes associated with it. So what do I mean by a random variable? A random variable is a variable which has outcomes, multiple outcomes associated with it, and each of the outcome have a certain amount of chance associated with it. So it's a random variable which is associated. Random variable. Okay. So a random variable is a variable, as we have already discussed, that it is a variable x which has multiple outcomes. Say there is a variable x which can give you 100, and there is a variable x which can give you mine, and the variable can also give you output -100. You see that there are multiple outcomes associated with this particular variable. Now, if it can give you 100 as well as -100, that means those outcomes do not occur at the same time, right? So, if 100 occurs, -100 would not occur. If -100 occurs, 100 would not occur. Therefore, this X is more like a lottery, right? And it is this lottery that we call a random variable. That is, there is an outcome, as there is a probability associated with each outcome, right? So there is lottery, and it is this lottery. So that means in a lottery there is a probability associated with each outcomes. Probability associated with each outcomes. And when probability gets associated with each outcome, that is where it becomes random. So what we say over here is that there is a probability associated with each outcome. Now what is this probability getting associated with each outcome? Now if there is a probability associated with each outcome, then what happens is the following. So, so say for example, I cut a lottery ticket, right? And I pay rupees 100 to get that lottery ticket. Now, if the lottery pays off, I'll get say perhaps 1 lakh. So the lottery ticket actually generates two outcomes. One with -100 and the other with +100, plus 1 lakh. And each of these have a chance of occurring. Therefore, this is called a random. So if I think about the lottery as a variable, which can give me two outcomes, 1 lakh and -100, then what I'm talking about is a simple lottery, right? So this is what a random variable would be. So if I want to create randomness, right, I have to create uncertainty in the behavior of a variable. And if I'm creating uncertainty in the behavior of a variable, then I need to ensure that one variable comes out with multiple possible outcomes. And this is very similar to a coin tossing example. If I toss a coin, I know that there might be a head, there might be a tail. But which is the one outcome occurring exactly in that toss is something which is there, right? So over here, the next thing that we would like to talk about is in this minor process, right? Now, the minor process is a more continuous kind of a randomness. Now, think about it like this: that there is a chance that say there are say outcomes. Any outcome can occur between 0 to -infinity to +infinity. So a variable is there which gives us any possible outcome. So that is what is continuous randomness. So bringing in a continuity in the randomness, this variable, there is a variable x which can take any value between -infinity to +infinity. That is, there is a variable value attached to it, right? So therefore, so over here, what we want to, or what we need to do over here is we need to understand that, okay, there is, so the variables work it this way. So, so over here, what we need to, so say for example, so let me just concretize this example once again. Say I have a variable x which belongs to minus infinity to plus infinity. So it can take any possible, kind of any possible outcomes between minus infinity to plus infinity, any possible outcomes, right? So therefore, and therefore with each of these outcomes, there would be a probability associated with it. You'll always have a probability that the variable in a particular trial will generate one outcome. Say today, there can be it generates just one outcome. Tomorrow it generates another outcome. So what does this randomness or what does this random variable represent in this asset equation? It represents the uncertainties that arise from the business. The uncertainties that arise in the business environment. Right, so this is what this is what is the part we call the uncertainties about the business environment. About the business environment. So over here it says that the asset price that I have over there is a function of the average growth in the asset price over time, plus the average dispersion, and the average dispersion, which is in turn affected by the random changes in the business environment or the uncertainties by the business environment. Because if you think about it, the business's asset prices, right, or the asset valuation would be impacted, or the variation in the business's asset values would be determined by the uncertainty in the business environment, isn't it? So say for example, if I think about let's think about the cash flow of a business as a asset, right? So let's think about this, that the business's cash flow is the asset. The cash flow of the business is the asset. The business is the asset. Is the asset. So cash flow of the business is the asset. Now this cash flow is, so every over a period of time there would be an average growth rate or the average rate at which the cash flow grows, right? So there is an average growth rate of the cash flows, and there is a standard deviation associated with it, right? Now there would be also a variation about the cash flow, correct? Now if there is a variation about the cash flow, right? If I get to see that okay, there is a variation for this variation of this cash flow and so on, then what are we supposed to do? So then what we intend to do over here is the following, that the cash flow changes due to uncertainty in the business condition. So when I see that the the cash flow changes due to uncertainty in the business condition, there I know that okay, this is how the thing should change, and this is how. So it is due to the uncertainty or the randomness in the business environment which is causing the cash flow of the business, right? So any evolution in cash flow, your cash flow will obviously grow at a constant rate or at an average rate. Similarly, there would be a randomness among the variations. And it is this randomness or the uncertainty in the business situation which will cause a variation in the cash flow. Higher the uncertainty, higher would be the variation. Therefore, if I want to understand how is the cash flow of the business evolving over time, I need to have an idea about the average growth of the cash flow and the overall or the average dispersion and the impact of the dispersion due to the uncertainty in the business. So it is this uncertainty in the business which is being captured by this variable, the WAT or the Wiener variable or the Wiener process. So WAT is considered to follow a normal probability distribution. It's a standard normal distribution with mean 0 and a variance t. So this, given the fact that I am drawing this WAT from a continuous from a continuous probability distribution, makes it a random variable, that these values, the value that this Wiener process is generating is being randomly generated from uh, the point. So that is what is W. So that is what is the Wiener process. So Wiener process is named after the person who had actually identified or described this variable. That is a WAT variable, right? So this is what your Wiener process is all about. Clear? See, so is the equation clear now, right? So if someone tells us to describe the asset price equation, so we be able to describe this irrespective of its mathematical perspective? So what we can see over here in this discussion is that this asset price path, right, is explained or can be explained in a very intuitive manner, and there is an intuitive logic more than a mathematical part which was used to create this equation. So each of these components which have been introduced in the in this asset price equation is interpreted in a kind of what should I say? It's interpreted in a kind of intuitive manner. So is this intuitive identification? I mean, is this intuitive interpretation clear to us? Any questions up to this point? Preeti, Karan, Vishal, Kumar, whoever is there in the session. Yes, Anirudh. Great. Okay. So now from here, we need to understand. So over here it shows the percentage change in the asset prices. Now coming to the next part of the equation. Uh, so what we need to know over here is that how is it that we will identify the probability of default from here? Okay, so Vishal has a question over here. I'll just take that up before I move on. So he asks that just for a confirmation, this equation reflects the asset price movements in an uncertain environment, right? Right, Vishal. That this represents a percentage change in the asset price, or how would the asset prices evolve, where it is where the asset price has an average rate of growth, constant average rate of growth over time, overall deviation, and there is a deviation in it, and there is and the deviation is also driven by certain business uncertainties. So in a way you can say that it talks about the asset price growth in, yes, in a situation where there are fluctuations which are driven by business uncertainties. You can say that. Great. So after this is done, right? So what exactly will be our probability to default? So the probability of default over here for a borrower is nothing but it is the probability that the asset of the borrower AI falls below the debt obligation in the next 12 months. So this is precisely my probability to default for IF borrower. Right? So this is the probability to default for the ith borrower. Clear? So now, what is the next ask that we have over here? What is the next big ask? The next big ask over here is that I can see that. So for this, I need to identify the equation on this. So what is the equation for AI, or what is the equation of the asset path? What is the equation of the asset? What is the equation of the asset? So over here, when I talk about the equation of the asset path, right? So what is this equation? So the equation over here is the following: that I need to identify, or I need to create this equation. So this equation needs to be derived. So this asset path, the borrower, needs to be derived. And from where do we derive this asset path AI? So this asset path AI needs to be derived from your this thing below. It is needs to be derived from this asset price path or asset price equation. The equation talks about the growth rate or the percentage change in the asset path, and from there we need to derive equation for the asset equation. I would say derive from the asset. So over here, what you can see is I need to integrate this part, right? And from there, I need to compute the asset price part or the asset price equation, as we may call it, right? So, guys, just give me 5 minutes time, and we'll just start back. Okay, fine. So, as we were saying that, so this is what the next thing that we need to do is we need to derive the equation of the asset price path. So over here, what you can see is, or what you can see has been defined over here, is kind of the percentage change in price, right? So from here, what we need to do is we need to derive, right? We need to derive the original or when you derive the asset price AT or AI, whatever you call it. So I need to know that what is the asset price or what is the so how would I determine what are the factors that would determine the asset price of a borrower at the TH time point. So over here, all that we can see is based on the so over here, it's not based on the percentage change. So all I can see is that these are the factors which affect the percentage change in the asset price. Now from there, what I want to do is I want identify the not the percentage change in the asset price, but I want to find out the change in the asset price, or I want to find out the path of the asset equation, right? How is it that the asset price equation is determined? What are the key factors in doing identifying that? So, for doing this, so what we need to do over here is we need to use something called. So this is a very famous equation. This is a very famous lemma in finance, known as Ito's lemma. So from a first order derivative equation, so if I have an equation which has in this form as a percentage change in price, right? A percentage change. So that is estimated, or that is captured, or that can be converted to obtain the asset price equation to something called Ito's lemma. So Ito's lemma is a equation, or it's a algorithm, or it's a or it's a mathematical framework which helps us derive the variable at, the equation path of the variable at, from this differential equation that we have over here. Now, from this equation, which shows the rate of change of uh, the asset price path, we can use the on this equation we can use the Ito's lemma, right? And from there, what we can do is we can actually identify the the path of the equation, Ito's lemma, right? So over here, Ito's lemma is something like what should I say? It's something like it's something like this. So it's a mathematical equation. So using this mathematical equation, we can actually get out the function. So over here, BAT by AT, or the percentage change in the price, can be defined as d log of AT. Now, why am I saying this is a log of AT or something like that? So before I go into the Ito's lemma concept, just let me ask you one thing. How many of you are aware of the basic concepts of derivatives? So what exactly is a derivative? How many of you know a first order derivative, second order derivative? How many of you have done basic calculus? Be it in your school days, your graduation days? How many of you? Okay. Preeti, Piyush, Vishal, Anirudh. Okay, great. So I'll just, before going into Ito's lemma, just let me give you a brief idea of what derivatives are. Otherwise, you'll not be able to get the idea as to how this model is developing. Okay. So over here, say I have a function like this. So there is a function y equals to fx. So what is this y equal to fx? So it says that this function is a rule such that, so y equals to fx is a rule such that, where you have, so given a value of the independent variable x, you will get a corresponding value of y. So x is your independent variable and y is your dependent variable, right? So over here, what we get to see is that, so basically if x changes, then y will also change, right? So this relationship or this specification talks about a mathematical causal relationship, causality. So this is known as a function. So what is a function? So a function talks, or what does function actually talk about? So function talks about a causality, about a causal relationship. So it talks about the concept of causality. How is X causing Y? So if X changes by 1 unit, what would its impact on Y be? Then by how much or what percentage will Y be changing? So this is known as causality. Right. Now after this, the next question that we need to answer ourselves is, then if X changes by a certain percentage, what would be the percentage change in Y? So this is the next check that we need to do. So if X changes by a certain percentage, what would be the corresponding change in Y, right? So over here, so let's take an example like this. X equals Y equal to 2x. So when X is 1, what is the value of Y? 2, right? When the value of X is 2, the value of Y is 4, and so on. So basically, whenever I'm trying to derive out, whenever I'm trying to frame out this x equals to 1, y equals to 2, x equal to 2, y equal to 4, and so on, that is where this entire idea comes in. Right? So that is where what I want to do is, I want to frame an understanding of this particular point, that x equal to 1 and y equal to 2, x equal to 2, y equal to 4, x equal to 3, y equal to 6. So every time x changes, y also has corresponding effect. So X causes Y to change, or a change in X causes a change in Y. So this is basically the concept of a function. So a function is a rule which explains the causality between X and Y. Clear? So this is what the overall idea is. Now, if I want to know that when X changes by 1 unit, what is the corresponding change in Y? So if X changes by 1 unit, X changes by 1 unit, when X changes by 1 unit, by how much does Y change? Y change. So X changes by 1 unit, then if X changes by 1 unit, how much by how much does Y change? So this is precisely what we are trying to do over here. Now, when we are trying to do this part, or when we are trying to, kind of explain this, the next question that would come to our mind is the following: that how can I capture this change in X and this change in Y? Now, the function of the part which covers the change in X and the change in Y. So this is, or the change in Y and correspond to change in X, is called the derivative of X, or derivative of Y at X equals to A. So let's see this. So for example, say I have the function y equal to fx, right? Now what happens is x changes by an amount delta x. X changes by an amount delta x. So this is called the change in x. Your change in x. And y correspondingly changes to an amount delta y. This is change in y. So when x changes by an amount delta x, y changes by an amount delta y. So how would this actually work? So when x changes by delta, so after x has changed by this amount delta x. Now delta x can be anything. Say 5 units, 3 units, 4 units, anything. So after x has changed by an amount delta x, the question that comes up over here is that by how much would y be changing? So y changes by an amount delta y. Say, for example, with change in x, right? So there is also a change in, there is a corresponding change in y. There is a corresponding change in y. So how does it look like? So after the change in x and y has occurred, it becomes y plus delta y is equal to f of x plus delta x. So y plus delta y, so that is where x plus delta x. So now what is the corresponding change in y? How do I identify that? So y is not change in y is nothing but delta y. This is f of x plus delta x minus y. So f of x plus delta x is the final value of y after changes happened, and the initial value was fx. So delta y over here will be right. So over here, delta y is this. So now, how is it that I can say, or how is it that I can compute the change in y that is expected when x changes by 1 unit? What would be the change in y corresponding to the change x by 1 unit? So over here, see, when x changes by delta x, the corresponding change in y is f of x plus delta x minus fx. So the corresponding change in x is f of x plus delta x minus fx. So if x changes by 1 unit, if x changes by 1 unit, then the change in y will be f of x plus delta x. Delta x. So when x changes by 1 unit, y changes by delta y, which is f of x plus delta x minus fx by the delta x. So basically in this equation, right, so in this equation, say x changes by 1 unit from x equal to 2, x changes by 1 unit. Now the question that comes out is that corresponding to this change in x of 1 unit, what would be the corresponding change in y? So change in y will be final value of y minus the initial value of y. Correct? So what will be the final value of y over here? So initially what I know is x was 2 and y was 4. Now x changes by 1 unit. Delta x is 1 unit. Or say delta x changes by 3 units. Let's do it like this. So then what is the change in y? So first of all, what we need to do is to find the final value of y. So to find the change in y, we need to identify the final value of y. So over here, the final value of y is so what will be the final value of y over here? So the final value of y is f of x plus delta x. So what was the initial value of x over here? It was 2, right? And then what I had was 3. So after change, the what I need to compute over here is f of 5. Now what is the equation over there? Y equal to 2x. So the final value of y final will be 10, right? So the value had increased from 2 to 5. So the value of y has increased from 4 to 10. So what is the change in y over here? The change in y is delta y, which is f of x plus delta x minus f of x. So over here what we will have is f of 5 minus f of 2. So this is so over here what we have is f of 5 minus f of 2, which is 10 minus 4, which is equal to 6. So over here what I want to do is I want to create this case. So this 10 minus 4 is equal to 6. So what I see is that when x has increased from 2 to 5, the value of y has increased from 4 to 10, which is it has increased by 6 units. Now comes the concept of this. So when delta x is equal to 3 units, what is the corresponding change in y? So the corresponding change in y is 6 units. So if x changed by 1 unit, that is delta x is 1 unit, what will be the corresponding change in y? It is delta y by delta x. So which is equal to 6 by 3, which is 2 units. Two. So for every unit change in x, y will change by 2 units. So this is what is the concept of derivative. So it shows the following, that delta y, change in y with respect to 1 unit change in x, is nothing but f of x by delta x. So over here, delta x is equal to f of x plus delta x minus fx by delta x. So this shows the rate of change of x, or rate of change of y, corresponding to 1 unit change in x. Now over here, the example that I have used, I have shown that the x changes by a large amount. It's quite a large change. So if x changes by, however, if the change in x is very less, if delta x tends to 0, that is, the changes in x is very small, right? Because the objective of calculus is to compute, or is to take up, or to identify the small percentage changes in x, right? So delta y delta x, so f of x plus delta x minus fx by delta x. Now what if this delta x is very less? So if it's a very small change, say x changes by 0.00023, so what would be the corresponding change in y? So that is why we are using delta x tends to 0. So what we say over here is that when delta x tends to 0, or when the limit of delta x tends to 0, delta y delta x is equal to by delta x. And for this very small changes of x, the rate of, when we compute the rate of change of y correspond to very small change of x, what we get is dy dx. So this is called the derivative of y with respect to x. So a derivative of y respect to x tracks the percentage change in y, or the rate of change of y with respect to change of x when x changes by 1 unit, or it tries to find out the change in y that we have respect to 1 unit change of x. So this is called the derivative of y with respect to x. So just a word of, just a small note, guys. Please note that if you are looking to work into this domain of credit risk, data science, etc., going forward, right, then it is absolutely necessary that you brush up your basic mathematical and calculus skills, right? So because be it these classical methods, or as we go forward, when we talk about optimization algorithms, So that is where the basic concepts of calculus would come in very handy, right? So when we talk about error minimization, when we talk about uh, minimizing the sum squares of errors, when we talk about minimizing the logistic regression equation, and when we are talking about optimization algorithms or neural networks or anything, that is where we need to have a clear cut understanding of these models, right? So this basic calculus portion has to be very clear in front of you. When if you are looking to make a career in credit risk or market risk or your data science, etc., so you must know, it's a must know, right? So please start brushing up these basic mathematical and statistical skills. The statistical side of things I'll take care of during the sessions, but the basic mathematical parts you have to be very aware of it. Okay, great. So over here, so this is what derivatives are, right? Now in tomorrow's session, we'll continue with Ito's lemma, right? We'll go and we'll visit the structure of what is a TTC PD, what is a point in time PD, etc. Right? So this is what we will actually take up in tomorrow's discussion. Okay, so in tomorrow's discussion, we'll be talking about the Ito's lemma, and we'll see how this framework goes in explaining the point in time PD and the TTC PD. So this is where this particular part would be that this particular part would be taking us to next, right? And over there, we'll discuss the details of the two rating philosophies that Basel talks about. So this much from my end for the day. Tomorrow again we meet at 9. Thank you. Bye bye.